Okay, gentlemen, I hope it was all well during your exam. You had good time in sessionals? Okay, I hope so. So I hope you would get your mark sheets for your quiz number 1, section number 1 and assignment, I think by this week, by the end of this week. I hope so. I'll try my best to complete it in time. Now I would just continue from the topic which we left a week ago, and that was about the PVT surfaces. How do we use those PVT surfaces to find out or analyze different thermodynamic systems? Now I hope I am audible at the back. Now I would solve, in this lecture I would solve few numerical examples, okay, and the purpose of solving those numerical examples is just to show you how to read the steam tables, how to use the values, and how to extract the information related to the systems from the statements, okay, and how to correlate everything with each other. So I have picked those problems from the book Moran and Shapiro, and generally in this course I am following that book, although there are other books as well. I have given you 3 references. You can pick any one of them, and the content is almost similar, right? So it may be the sequence, one topic is coming first and the other one is coming at a later stage, but somehow or the other I think they are similar. So now I would solve few problems, and then I would also show you how to read these statements, how to extract the relative information, and then how to read the values from the steam tables. Okay, so this is where we left before sectional exams. So if you look at this statement, a vertical piston cylinder assembly containing 0.1 pound of ammonia, right, initially a saturated vapor. Now this is very important. Just whenever you are reading that statement, you should be very much sure about those identifications of the regions on that PVT surface, right? So you should consider those surfaces into your mind and just consider that you have got every information related to the aspects of those projections and PVT surface, and then try to relate all the statements with that. Now, for example, if I ask you, this is initially a saturated vapor. Now, can you imagine where that point would be lying on that PVT surface? Can you imagine that? It's a saturated vapor. It means if you just look at the vapor dome, I hope you understand that this is kind of the vapor dome surface. So it should be somewhere there, isn't it? So straight away you should think about it. Okay, is placed on a hot plate. So when this ammonia cylinder is placed on a hot plate, it is basically somewhere lying over there on the saturated vapor line of the vapor dome, right? Then due to the weight of the piston and the surrounding atmospheric pressure, the pressure of the ammonia is 20 pound-force per inch square. So pressure is also given. Heating occurs slowly and the ammonia expands at constant pressure. Now just think of those lines which are known as isobars. You remember? Once you talk about this TV surface, for example, if this is the TV surface, I hope you remember that these are the isobars, just like this one, right? So these are the isobars. So whenever you are talking about the constant pressure, it means the process is going over this line. Okay. Heating occurs slowly and the ammonia expands at constant pressure until the final temperature becomes 77 degree Fahrenheit. Show the initial and final states on TV and PV diagrams and determine first the volume occupied by the ammonia at each end state in feet cube, the work for the process in BTU. If you are talking about a constant pressure process, what would be the work done? Do you remember that? P into, just think of it, work definition is what? Integral P dV, right? If pressure is constant, so that would be what? P into V2 minus V1, simple as that, right? So just think about it. Now, this is the first thing, that show the initial and final states on TV and PV diagrams. Now, this is a TV diagram and this is a PV diagram. They look similar. The only difference is that once you talk about isobar through this vapor dome, it goes like this. This is an isobar. And similarly, once you talk about the PV surface, PV projection, those isotherms go like this. These are the isotherms. Right? I think this thing should be very clear. Now, just talk about show the initial and final states on TV and PV diagrams. Okay, just tell me, if this is the TV diagram, the initial state is what? It's a saturated vapor state. So where would your point lie? Somewhere here on the saturated vapor line. This is the saturated vapor line. This is the saturated vapor line. So your point is somewhere over there, right? And this line is having a pressure of what? 20 pound force per inch square. So this pressure is 20 pound force per inch square. Now the point is, how can I determine temperature? I mean, this is the pressure. Okay, fine. This isobar is giving me a pressure of 20 pound force per inch square. Now, how can I find out the temperature on this isobar, or let's say for this state 1? Okay. Now, if you remember, I told you there are steam tables. There are steam tables, and this is because describing a state of saturated vapor line. So I talked about two types of steam tables before the sectionals. Just look at that. Tables are given to you, and generally on top of the table it is given that what kind of table it is and for what kind of substance it is being used. So you can see this is superheated water vapor, isn't it? It is basically occurring at the saturated line, saturated vapor line. So I hope you remember that superheated vapor region starts from that saturated line. Did I show you that before the sectionals? I think I have shown that, right? So just go back, and by the way, these tables are related to the SI units. Let's go to the tables with British Engineering System units, because we are talking about those things. Yeah, this is for English unit. Just see, this is for superheated water vapor table. So it is on page 979. Let's go to that and see. Yes, this one. Now, what was the pressure? It was 20 pound force per inch square. Now, what is the saturation temperature? What is the saturation temperature? It is what? 228 degree Fahrenheit. That's what it is. Okay, your question. Oh, I'm sorry. Yes, this is for ammonia. Thank you so much. This is for water. We should go for the tables related to ammonia. Thank you. Yeah, this one is for refrigerant 22, and then we need to see. This is for refrigerant, and again let's go for the ammonia. Yeah, this one. Thank you so much. So this is for ammonia, right? Because you can see for every substance you have a different set of tables. So if you go for this 20 pound force per inch square, what is the saturation temperature over there? It is minus 16.63 degree Fahrenheit, and you can see this sat means it is talking about the values at the saturation temperature, right? So just see that what is the temperature over there? It is minus 16.63 degree Fahrenheit. Okay. let's see. And then we need to see the volume occupied. By the way, this is the first step. We need to see the volume occupied by ammonia at each end state. Or did we show the final? Okay. Now, this was the initial state and it was a constant pressure process. The system goes to the second state, which is the final state, through a constant pressure process. So I mean, this system has gone along the isobar, isn't it? This isobar is going what? Is showing what? 20 pound-force per inch square. So it goes along this thing. So you can say that somehow or the other you have reached this state. And if you have reached this state, what would be the physical condition of that vapor of that water? This would be kind of superheated, isn't it? This would be kind of superheated. So you can say that this state 2 is giving you superheated vapor state. Do you understand this thing? So you can see that it is basically coming from what? The understanding of the PVT surface or TV surface. So this is, it means if you go along the isobar, so you have reached to a point which is in what region? Superheated vapor region, right? And then now the point is, let's jump onto this thing, the volume occupied by ammonia at each end state. So it means you need to find out volume occupied by ammonia at each end state. Now, do you remember something about this specific volume? What is that? This is volume per unit mass. Now if I ask you system is there at this point, it is basically generally the states at this saturated vapor line. This is saturated vapor line. So these states are represented with a subscript G generally. Okay, in all the books you would see this thing, that generally the states lying on that saturated vapor line, they are basically represented by what? A subscript G. And those lines, those states which are there on the saturated liquid line, they are represented by subscript F. Okay, generally this is the notation, and you should understand whenever there is written this is Vg, you should understand that this state is lying at the saturated vapor line. If it is written as Vf, it means something is belonging to the saturated liquid line. Now, if we talk about this volume, I know the mass, isn't it? 0.1 pound is given to me. I know the mass. Now, if somehow or the other I find this V, which is the specific volume, I can find out total volume. Do you agree with me? Now, let's go back to this one and see what are the properties which are given there. This is V, small v. You would see that small v, internal energy, enthalpy and entropy, they are given in those tables. Those four properties: specific volume, internal energy, enthalpy. Now what are those properties? Enthalpy and entropy, we will talk about that later on. But you know at least what is internal energy and what is specific volume. Okay, so specific volume, this is V. So if you talk about this 20 pound-force per inch square and the saturated temperature is minus 16.63, so can you see that this 13.497 would be the specific volume at that saturated line, at that point on the saturated vapor line? Can you see that? So now it means V1 would be equal to what? 13.497 497 feet cube per pound. Is it understood? Is it understood or not? Okay. Now, the point is, let's go back to, I'm sorry. Yeah, let's go back to this thing. Just look at the second state. On the second state, your temperature has increased, isn't it? Pressure remains the same, but temperature has increased. Now, just look at that table and tell me, can you guess now where is the temperature? You only know the first saturated temperature because it was lying at the vapor line, saturated vapor line. Now, can you tell me how would we determine the second temperature? Sorry? 70 and 80. Why should I do that?
It is like points can be taken as a point forms like a linear graph, and when you go between temperature 70 degrees.
Now, graph is what? I'm sorry, just repeat. This is what, 16 point? And what are the units? Feet cube. Okay, so you know the volume occupied by ammonia. You know V1 and you know V2. So both the steps are covered. You know V1 and you know V2 now. Let's talk about the second thing, the work for the process. Come on, how can you find that out? Yeah, exactly. This is only, this work would be like from V1 to V2, and this is PdV. This is the actual definition because it's a constant pressure process, so you can simply say this is V2 minus V1. Now, by the way, how to go from this smaller V2 to capital V2? You just multiply it with mass. Okay, how to go from smaller V2, which is the specific volume, to the capital V, which is the volume, actual volume? You just multiply it with M. Understood? Any question? I mean, this is quite tricky. If you understand how you go along the lines, isobars and isotherms, you can identify the regions, you can think of the problem, what is physically happening inside that system, and then you can effectively read those tables. Right? So in these kind of studies, either you get everything, you understand everything, or you do not understand anything. Okay, so everything is kind of interrelated. Okay. So let's move on to the second problem, which is this one. And before doing that, did we define quality last time? So let me define one equation. Now just try to understand this equation. What is the purpose of this equation? For example, this is PV surface or PV surface, whatever it is. Now the point is, on this line you have value Vf, on this line you have value Vg, and somehow or the other these two values are defining the densities, because this Vf is what? This is basically 1 over rho f, isn't it? This Vg is what? This is 1 over rho g. So just be very careful. The point is, if some state is lying over there, obviously it would have an overall density or overall specific volume. Do you understand my point? Now if quality increases, total V remains the same. Total V remains the same along that line, is it? So I am repeating my sentence. Just look at the plot and tell me if does total V remains the same along this line? Not at all. Why? Because you are going along this line in the horizontal direction and it is changing. It is changing. So it is going from Vf to Vg. So obviously it is increasing. It is increasing. Now if it is increasing, my point is how would you be able to find out some V over there in between Vf and Vg? Right? So this is done by defining quality. I hope you understand the question. I am going really slow because these things are hard to understand, a little you can say tricky, so just ask question if you do not understand anything. The point is that you have Vf at the saturated liquid line, you have some quantity with the subscript G at the saturated vapor line. Now if you are lying somewhere in between in the vapor dome, how can you find out specific volume, or let's say internal energy, or let's say enthalpy, or let's say entropy within that vapor dome? Now my point is you do it by the definition of quality. You do it by the definition of quality. Now what was the quality? We defined it. How much portion of the total substance has been converted into vapors? And if you remember, we defined it like this. X is equal to what? Over total M. That's how we defined it. Do you understand that? Okay. Now, if I start defining this total volume, what would be the total volume? Total volume would be volume of the liquid plus volume of the vapor. That's how you can define it, right? Now if I try to define this smaller v, this would be equal to total volume divided by mass. This would be equal to V liquid over M plus V vapor over M. That's how I can define it. Now this V liquid, this capital V liquid, this M is total mass. Just look at that definition. This is total mass. Okay. So this smaller V is equal to V over M. So can I write this thing as M liquid over M V plus M vapor, sorry, this is M vapor over M into some V? Can I write it like this? Do you understand what I am writing? Okay, ask question. Who said that? Ask question, come on. Yeah. Now, do you understand this thing? If you are lying inside the vapor dome, our point is what? How to find out the properties inside the vapor dome? That's the question, right? Because you know how to find out the properties at saturated lines, vapor line and the liquid line. But my point is how to find out the property inside that vapor dome, right? So we want to do something to use that Vf and Vg to find out the property inside the vapor dome. And we would associate those Vf and Vg with quality so that we can find out an equation to look at the properties inside the vapor dome. That's the question. Now, can I write this V, capital V equals V of liquid plus V of vapors? Because if you are lying inside the vapor dome, there would be some portion which is vapor and there would be some portion which is liquid. Do you understand that? Now I can write this thing. Now if I divide this total volume by mass, can I write this equation like this? Now do you understand that? Now the point is, if I write down this V liquid as M liquid over M into V, I would come to that point. Now my point is, if it is V liquid, So should it be V liquid then? Now this V liquid can be written as M into V liquid, sorry, smaller V liquid. Now what is that smaller V liquid? Isn't it the saturated vapor specific, saturated liquid state, specific volume at the saturated liquid line? So this can be written as Vf. And similarly this vapor can be written as, this V for vapors can be written as V of G. Now do you understand that? Now that's the point. Now this M liquid over M, we define this quantity as what? X. If this is X, this would be what? Isn't it? This would be what? 1 minus X. So from here you have got this equation that this V inside the vapor dome can be found out by 1 minus X into Vf plus X into do you understand that? So this M liquid over M, okay. If you talk about this M, total M is what? M of liquid plus M of water, sorry, M of vapor. If you divide it by M, this would become 1. If this is X, what would be this equal to? 1 minus X. Understood? So this is the equation. V equals 1 minus X Vf plus X into Vg. So remember that this equation is valid for internal energy, this equation is valid for enthalpy, this equation is valid for entropy as well. You talk of any property within the vapor dome out of these four, this equation is valid for that. For example, if I ask you that you have some Uf and Ug instead of Vf and Vg, you can find out the internal energy at any point using the quality, right? So this quality definition relates everything to give you the property value within that vapor dome. Okay, remember that. I hope you understand that. Any question? Okay. Now let's solve this equation, this problem. Now look at this statement very carefully. A closed rigid container. Now what does that mean? That volume is not going to change. It means V1 would be equal to V2 straight away. Just look at the English and try to translate it into maths. Okay. So a closed rigid container of volume 0.5 meter cube. Volume is given, so it means you have V1 and you have that V2 as well. You have this V1 and you have this V2 as well. Okay. Is placed on a hot plate. Is placed on a hot plate. Initially the container holds a two-phase saturated liquid water. Is it lying inside the vapor dome or outside the vapor dome? Inside the vapor dome, right? So two-phase saturated liquid water and saturated water vapor at P1 equals 1 bar. P1 is given to you, okay, with a quality of 0.5. It means X is given to you. Okay. Now after heating, the pressure in the container is P2 equals 1.5 bar. Now just think of it. For example, if I am trying to plot a TV projection for this is the vapor dome. This is the vapor dome. Now these are the isobars. For example, this isobar is related to P1. For example, this isobar is related to P1. It means if I am talking about state 1, it should be somewhere there inside the vapor dome. Do you agree with that? Now, once you talk about the second state, it has increased its pressure. It means the process is not on the same isobar. It has jumped on to the next one. So it means let's talk about some other isobar, and this is the state 2, and this isobar is related with P2. Do you understand that? Now, can you see that I have drawn this circle right on the top of this cross? Why is it so? Exactly, volume remains the same. If volume remains the same, it means it has gone straight away up. Do you understand this thing? Now, after heating the pressure, okay fine, after heating the pressure in the container is P2 equals 1.5 bar, indicate the initial and final states on a TB diagram. Do you understand this thing? Done? Okay. We need to find out temperature at state 1 and temperature at state 2. Now, which table we should go to? The table which belongs to the two-phase region. We are talking about this water. We are talking about SI units. So, let's move on to those tables. Just give me some time. Let me go to that table first, and then I would. This is for saturated refrigerant. This is for superheated water vapor. Oh, just see. This is for liquid vapor region. Right? This is for liquid vapor region. Now, this is also for liquid vapor region. The only thing is this first column, only difference. The first column is related to temperature in table A-2, and in table A-3 the first column is related to the pressure in bars. Okay, if you have the value in pressure, for pressure just go to table A3. If you have the value for temperature, go to table A2. Okay, so now the point is, let me see the thing. We need to find out temperature in degrees centigrade at state 1. P1 was 1 bar. Now P1 1 bar. Now what is temperature there? 99.63. 99.63. Then your P2 was 1.5, and according to your analysis, you should be within that regime, isn't it? You should be within that regime. What vapor dome? You should be lying within that vapor dome. So if it is 1.5, what should be temperature? Triple 1.4. Do you understand this thing? Okay. Now the mass of vapor present at state 1 and state 2. Now this is about mass of vapors. Come on, think about it. Now you know how to find out those values. You have a question? Okay? You are not audible. Can you please? Okay, let's do that. Now can you tell me what is the mass of the vapor at that state 1? Come on, tell me what is the mass of the vapor at state 1? You know what is the volume? Sorry? Now this is for VF. This is for VF and this is for VG. Can you find out V? You know quality, you know VF, you know VG. Can you find out V at state 1? Find that out. Value comes out to be V1.8475. Okay, let's talk about this V2 now. We need to find out this V2. Look at this thing. Sorry? Why is it so? Volume is constant, exactly, but something changes. Something changes. Okay, the mass of the vapors, fine. We are talking about the mass. Volume remains the same, but mass of the vapor would also change. If you look at this line, just think of it. It was there, so obviously the quantity of vapors would be somewhat low at this point. The quality of the vapor at this point would be what? 1, isn't it? Because at the saturated line, everything has been converted into vapors. On the saturated liquid line, X would be equal to 0. So just think of it. You need to go from 0 to 1. You need to go from 0 to 1. If this quantity is 0.5, would it be equal to 0.5? Not at all. Right? So think over it. Tell me. Now you have what? You have V2. This would be exactly equal to 0.8475, and then you have P2 as well. This is equal to 1.5 bar. Just remember, I told you once we were talking about those PVT surface that inside the vapor dome you need to have at least 2 properties to determine the state. Do you have those 2 properties? You have pressure, you have volume. Now